and Fuji are ready to join you live. So let's get this party started. I'm going to make some tea and wait for everybody to join. So here we are. Here we are, Baji. Say hi. Hi. Hi, everybody. Good evening, good morning, good afternoon. We are here with one more live stream. We're going to talk about physics. We're going to catch up. We're going to chat. We're going to hang out. I know it's a late night live, but it could be a different time in a different part of the world. So we try to catch everybody. And here we are with one more live. Thank you so much. We'll get this party started. Okay, here we are. Okay, here we are. So I am pretty much ready. I have already eaten my noodles for the day, and at this point, it's pretty much we're good with most things. I just might make some tea as we have people join. I know it's pretty late on the East Coast of the United States of America, but there are other parts of this world that sometimes do join us, and therefore we are, there's my live, sorry, 1 second. I have to make sure that the live is working on my other device, and sometimes that takes me a moment. So how is everybody doing? If you're seeing this as a video upload later on, under the live tab of the channel, thank you so much for joining. Thank you so much for watching. Please do watch till the end. That helps us a lot with YouTube and whatnot. And thank you for being here. I'll leave some comments myself so that, or some chat messages myself so that I know that it's working. So yeah, we will do our chats and physics. Now I understand that people might be sleeping, but you know what? We'll give this a try. Okay. All right. Thank you, everybody. How are you? Ready for some physics jams? So we are over here, and we will get this party started. So let me know in the chat how you're doing, how's everything going, and we will discuss, or we will continue our quantum mechanics discussion from last night. So where we were last night, we just were reading about the great debate between Einstein and Bohr. And even though it seemed like Einstein had won that argument, Bohr went and spent a sleepless night. And Baji the handsome cat. Hi, Sioleka, how are you? It seemed like Einstein had won that particular argument, but it sounds like Bohr actually went and spent the whole night to kind of think through what he was going to say, what his reasoning was. And hello, it is I. This is the kitty cat / person that's talking, me. And over there is Baji. How are you guys doing? I'll say hi like this for a second before I go off to make my tea. Hi. Hi, Sioleka. Hi, Death Dragon. So, last night we were seeing that Einstein and Bohr are two very different people, or were. Unfortunately, they're no longer with us, but they were two very different people, and they had some major achievements. There were some developments going on in quantum mechanics that was making a lot of very important scientists who themselves had contributed to quantum mechanics very uncomfortable, because quantum is such. But then it's interesting because some of these contributions that people made also made room for other people to contribute. Hi, Michael. I don't know what that means, but thank you for the question and the comment. There were, even though there were some problems or some discomfort with these developments and these progresses in quantum mechanics, especially because it was such a weird topic, it was such a, well, not weird, but fascinatingly different kind of. Oh, good job, Michael. I think that's a good idea. You can chat message something else if you'd like. Even though. Heike, are you here? Mr. Finland. UK. Hey, Google, what is the time in UK right now?
The time in the United Kingdom is 6:23 a.m.
If my friends from the UK do not join, even though it's 6 in the morning there, which is pretty much a reasonable time to be up, then I'll be very upset because I'm doing my best here, guys. I'm doing my best. If you see this later on, my UK friends, please do say something in the comments so that I don't completely depress myself. So, as I was saying before some weirdness happened, it's 1:24 for me. Oh, good. Thank you, Death Dragon. Thank you so much for being here and for being so active in the chat and telling us the time. It is the same time for me. So, we must be on the East Coast together. I'm calling from Boston or joining from Boston. So, basically, this is where we were at. This is where we were at. It was very difficult for physicists to accept that physics in the quantum world was no longer deterministic. Physicists were kind of obsessed with control. They wanted to be able to write down an equation and basically predict the future forever. Basically, if some equation gave you the position as a function of time, say, for example, for the moon or something like that, that meant you could kind of predict the position of something like the moon or a comet or a planet forever, like say for the next many, many years. Death Dragon says you're welcome. Yay, awesome. For me being active, thank you. So basically, this is what people were used to in classical mechanics. My neck hurts. This is what people were used to in classical mechanics. But then there came progresses in quantum mechanics. And remember, Einstein was an old contributor of the old quantum mechanics because he came up with photoelectric effect, or at least he contributed in a big way to photoelectric effect, and came up with this concept of light also having a particle nature, and that particle nature of light, when you put that on, shine light on metal, you can get an electric current out. That's how we can have something like solar panel. And this is also what he got the Nobel Prize for in he did this work around 1905, but I forget exactly. I think it was much later that he got the Nobel Prize for it, because he was more famous, remember, for special theory of relativity and subsequently general theory of relativity. The relativity guy, that's who he was. And a lot of people didn't really understand relativity. A lot of people even now don't understand it. So back then it was sort of those controversial type of things, and people were not sure, should we give this guy a Nobel Prize or not? Who knows? Like, what if it's wrong? But then eventually, I think they got it eventually he got it. He absolutely got the Nobel Prize, and not only that, he got it for a more safe topic, I think, which was the photoelectric effect. And by the way, we've been reading this book called Einstein's Cosmos by Michio Kaku, which we will continue reading in just a moment here. I wanted to give you a recapitulation of what we've been kind of talking about. And thank you for being here. So I'll continue. Basically, Einstein was one of the old contributors of the old quantum world. But as the 1920s and 1930s progressed, quantum mechanics started to see some very weird, so-called weird to them at that point, even sometimes weird now, depending on if you're up to date about it or not, progresses or developments that were very unlike what physicists knew to be comfortable with. I also sometimes think that if physicists didn't have an ego about certain things, would we have seen more progress sooner? Because sometimes you just have to swallow your pride and be like, oh, this is actually kind of shocking to me, but maybe nature is shocking. Maybe there is not everything is going to be so smoothly understood by me. Maybe something will be discovered that is uncomfortable. Being uncomfortable, sitting in your discomfort and being like, okay, also I liked and sub. Thank you so much. Thank you. Thank you for being here. Please join us again and again. We go live often and we've been covering these physics topics. So thank you so much indeed for being here. And it's a cat channel, but we also cover physics. And all my shorts and videos have kitty cats in them most of the time. So thank you so much. So it was hard for them because up till then, physics had been deterministic, predictable, as in an equation gave you a prediction for the future, and you kind of, as a physicist, was able to give people answers with some level of confidence, with a certainty. Everything that was quantified was deterministic and sort of certain, unless, of course, you had experimental error, which then you reported with a plus or minus uncertainty type of thing. But even that uncertainty was sort of certain in the sense, okay, I have experimental error. I know I cannot, measure something up to, I only can measure it up to this plus or minus error is how people would report uncertainty. Uncertainty was not something that came out of theory, for example. It was experimental error. So when in quantum mechanics, not only did the development give us probability, now we had probabilistic answers about nature and about where a particle is as a function of time. It's a probability is the answer. The answer is not something that you write down with certainty. It's a probability that you can write down. It's probabilistic. It's not deterministic. This really, really, really shook people. Hi, Bon Bon. Hi. How are you? Is this Yash? Hello to Pakistan. How are you? Not only was it probabilistic, that's the best you can do. And if something, so not only was it not deterministic, you have to swallow that this is probability. You only know the probability of something. You don't know the actual something where it is. You just know the probability of it existing somewhere, such as the position of an electron within an atom was a probability, was given with a probability. Okay, the probability of finding the electron, not the electron, but the probability of finding the electron. This was hard. This was very disturbing for everybody. Even Heisenberg, when he was hearing about what Dirac did, which Dirac wrote down the relativistic equation for the wave equation of matter, which was initially written down, of course, by Schrödinger. Even Schrödinger and Dirac, these people, they contributed to quantum mechanics, but then even they didn't like it anymore afterwards when it went in a certain direction. And Heisenberg didn't like it at first when these things were happening with the wave equation being written down and Dirac making it relativistic. But guess what? Heisenberg is the one who came up with the uncertainty principle. He's the one who quantified the uncertainty of things. Like when you say that something is probabilistic and that's the best you can do, then you should also say that actually there is uncertainty for this. And because there's uncertainty for this, you should be able to say the math of what the uncertainty is. You should be able to quantify. So now people were quantifying probabilities and uncertainties, and there was formalism given to this uncertainty with the uncertainty principle by Heisenberg. So now the same person who had his issues with quantum mechanics and his issues with what Dirac did because it was too crazy was actually quantifying and theorizing, giving us the formalism for capturing the same uncertainty that is inherent to quantum mechanics and to nature at that quantum level. When you shine light to measure an electron, you disturb it. So you cannot know both its position and momentum. Baji is coming here with his dog toy. Hi, Baji. Kolyash pe. Hi, Baji. Baji also wants to know about quantum mechanics. Come, Shona. Kolyash pe, babu. Oh, Baji. Oh, Baji. Come, baby. Ashbe kole, Shona. Okay. Baji does want to come to Kol, which is the lap. So, hi. What should I do, man? Do you want to come on my lap or not? Hi, baby. Shono. So this topic makes me very happy, so bear with me. I hope you stay here all night. Because it's been very entertaining to read about physicists' reaction. So anyway, once uncertainty was formalized, the same people who contributed to quantum mechanics like Schrödinger and Dirac wanted to have nothing to do with it anymore. Because they were like, oh my God, have we contributed to a theory or a physics which leads to probabilities and uncertainties? You're telling me you can't know for certain where an electron is? And Bohr was like, yeah, man. And Heisenberg was like, yeah, man. And I'll even give you an equation for the uncertainty because that is the uncertainty inherent of nature, not because I can't measure it well enough, but because that's what nature is saying. You can't measure nature at the quantum level with certainty. There is uncertainty as part of it. And in fact, I will even give you the formalism for this, says Heisenberg and Bohr, and Einstein debated Bohr. So we will read about that in just a second here. So it's very, very interesting indeed. Hi, Baji. That was, hi, Baji, come to lab, baby, come. He wants love, but he's also not settled down yet. This is a Baji cat, not Schrödinger's cat, because Schrödinger's cat was very controversial. So we will actually read about this debate and about Schrödinger's cat in just a second here. Thank you for joining. Thank you so much for being here. I'm actually, can I make some tea? Will you still be here? I just want to put the kettle on it's Baji, yeah. I just want to get the kettle going so that I can have the tea going and then, or the water boiling, which is very short. And then I can keep talking to you and reading. So let's do that. Okay, bear with me, don't go anywhere. Stay. Oh, here, let me show you where Baji went. He has gone to observe his quantum toilet. Baji has an automatic toilet. It may or may not be cycling right now. And to measure that, he has gone to the bathroom. So that's what's going on over here. Heike, are you here? Oh, also, let let me show you. This will be good. Let me show you the book. Yeah, I'll still be here. Oh, thank you, Death Dragon. Thank you so much. Love your support. Let me show you the book that we've been covering as well as my kettle starts to boil so that you can take a note of what exactly we have been reading here as a booktuber. So we've been reading this book called Einstein's Cosmos by Michio Kaku, how Albert's Einstein vision transformed our understanding of space and time. So this is the book that we've been reading and discussing from. And so we will actually pick up from this in just a second here. It's actually very interesting. We are learning lots of topics. I also went to, school for physics, of course, for all my different degrees. So I also add a lot of context from my own experiences and my own understanding of physics. We're mainly covering 20th century physics in these live streams so far. I've promised people that we will also get into the 21st century physics, which is the more current and relevant physics of today. But I think that by covering these 20th century topics, we're actually building a very solid foundation for what is to come going forward. So thank you for being here, and give me just a second. Sorry. Just got too busy at night and I did not boil the water yet. So I'm just doing that now so I can have my tea while we discuss and read from this book, Einstein's Cosmos. Yay! I've had this book for a very long time. Some of the pages have gotten yellow. I just went to the gym, I came back, I did some chores and stuff, so I just never made my tea. So I'm doing that right now so that I can sip something. Bon or Yash never responded whether that's Yash or not. My suspicion is that this Bon is actually Yash, but nobody said anything anymore, so I just see Death Dragon. How nice. Okay. Tomorrow I need to start this live a lot earlier, and I will. My plans are usually on Friday. I started sooner. I started more earlier in the night, and I have 2 McDonald's chicken nuggets. Should I eat left, right, or both? You should eat both, for sure. Go ahead and eat both, Death Dragon. We support this. Basically, tomorrow we will start this same physics week. I'm calling it Physics Friday Night Lives. And I will start it like more early in the night so that it's not so late and people have already gone to bed. But yeah, join us tomorrow as well. It'll be really fun. And usually I get a big crowd at that time. But then I today thought I will go live again and do this. So look at this tea that I'm going to have. It's called Quick Tea. It's a ginger tea. See, I got this from an Indian store near me. Quick tea, ginger, instant chai, latte. Just add the hot water and then it will make this tea for me. So Yeah, that's what I'll be drinking. Thank you once again for being here. Let me get my blanket ready. I know what it is. Once I get my blanket ready and I settle down on the couch with the book, then Baji comes and sits on my lap. I think he was trying to say that it's not comfortable enough for him on the couch yet because I didn't have my blanket spread out on my lap. So he was being a little particular with how he wanted lap time. Oh, sounds yummy. Yes! Thank you, Death Dragon. I kind of shake it like this so that all of the particles can fall to the bottom due to gravity. And then I can mix it. I can put the water in the mug to mix everything together. So yeah, here I'll show you. I just put, see my mug? Just put all of this in there. I make sure, oh, thank you. Death Dragon says, I love your channel. Thank you so much. Thank you for being here. Really appreciate you. It's a very good live too. Aw, thank you. It's peaceful. It's like tea and kitty cats and Einstein and books and quantum mechanics. I think it falls under peaceful, soothing content. So thank you for being here. It's a good night live because you can even turn this on and fall asleep if you like. We won't be offended. Because it's quantum. It's quantum and we will talk about it. So I put a little water in this to get the last bits of the tea out of the bag or the plastic, thing it was in, packet it was in. And now, ooh, I forgot to show you this. Look at my blue light teapot / water boiling pot. It boils really fast. I got this off of Amazon. It's not sponsored, although they should sponsor me because this tea appears a lot on this live. Oh wow, that's really cool. Thank you. Thank you so much. I love watching the little bubbles. Look at that. There's a phase transition happening here as the liquid water boils over and gives us boiled water and some vapor. Yay! Yay, thermal physics. Hi, Shona. Ki hoche, babu? Baji. Oh, look at Baji. He's playing. Baji? Bubbles. I love bubbles. Yes. Dead Dragon said, I love bubbles. Lots of bubbles here. Look at that. Wow. So many bubble. Ki hoyeche Baji? Ha bolo babu? Baji, no, don't try to. No. Water's boiling here, Baji. Don't try to jump up to the counter right now. I think Baji thinks that there's something exciting happening that he wants to see. But Baji? Hi Fuji Shona, kiyo babies. Oh look, there's lots of bubbles now. This is where the water has changed phase. Look at that. As soon as the phase change happens, the blue light goes away. There's my tea coming. Guys, I gave you a physics demonstration during this physics chat. Thank you, Death Dragon. Baji's so cute. Aw, well, he is here. Getting into trouble. You're so cute, baby. What's wrong, Baji Babu? What's wrong? What's wrong? You're okay. Look at you. Look at you getting butt scratches. You're okay. You're okay. Yes, you are. Yes, you are. You're gonna be okay. We're gonna read quantum really very soon here. Okay, Mama will make the tea and go sit. He wants me to go sit on the sofa and settle down. So then I just unplug this. See, it's done. I bring it over here. I make sure this is out of the way here. I don't leave anything unplugged or plugged in rather. I don't trust anything plugged in, so I just make sure it's all, good, unplugged, so kitty cats don't get into trouble, because there's some people here, some kitty cats here that like to investigate various nooks and crannies. He's on top of the fridge now, of course. Why not? Why not? Hi, Baji. Hello, say hi to your fans. This is your channel, Baji. Please do. Baji. Baji. Baji, Baji. What's up, Baji? Are you gonna say something? Are you gonna say something? And here's, of course, my Fuji Babu. Fuji Baba gets big kisses because, just because. Hi. How did Baji get up there? What do you mean? He just jumped up from here to there. He just jumped up. He just jumped up. He's a ninja. You should see Suji. She can jump up all to the ceiling through all this. Kitty cats can jump. He used this counter to jump up, but they can jump up very high. Dinosaur, you jumped. You jumped. Okay, I'll finish making tea and we'll go read Einstein's Cosmos. Oh, let me show you. As soon as I add the water, what does it look like? It looks like this. I have to make sure I don't accidentally spill anything here, but yeah, it's as simple as that. It's a instant chai mix that I get here in Boston. All right, Baji, are you ready? All right, Baji, are you ready? Ready for some physics time? Heike, are you here? Okay. Okay, we'll get started. Either way. All right. Come, Baji, we'll go sit. We'll go sit. Death Dragon says hi, Baji. Yes. Yes, indeed. Okay. All right. Let me just make sure everything is off and not plugged in. Nothing is... Everything good? Yes. Off, off. Off, 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 and off, and off. Yes, indeed. Okay. So as I was saying about quantum mechanics and its various developments, we've already met some important people and contributors to quantum mechanics at this point in the chapter. we actually met Schrödinger, who gave us the wave equation, of course, of particle or matter. At that point, we didn't know that it was going to be a probability. We thought, well, we've embraced wave particle duality of things, of light, so why not of particles as well? And he basically gave us a way to write down an equation that would describe the position of a particle, such as an electron within a hydrogen atom, as an example, as a function of time, which is very powerful indeed. Very powerful indeed, because we can then do quantum mechanics. Quantum mechanics is nothing but mechanics of the quantum level, just like classical mechanics is often to do with mechanics of classical objects like the moon, a comet, a planet, me, you, more classical things. Quantum is the physics of a very small scale. So we would need a different type of mechanics for this. And I knew it. It's all to do with this blanket. If the blanket's here, then he's happy. Physics of the very small needs a different type of mechanics known as quantum mechanics, and a different way of writing these equations, a different type of math, a different realm, which can be formalized and was formalized by Schrödinger. And then Dirac gave us the relativistic way of writing these things down and formalizing all of this. And it was all very good. All very good indeed. Okay. But then there were some difficulties being experienced by people because it led to Max Born finding that it's actually not the position itself of that electron that we wrote down. It is the probability of finding that electron. And then this probability stuff led to the uncertainty principle by Heisenberg, and Bohr contributed some things as well, some very important things with regard to, for example, the hydrogen atom. And people were very confused because they were not used to dealing with uncertainty and accepting that uncertainty is part of this game now, is part of nature now, and how we measure nature. And it's not an error due to an experiment, but inherent in nature is this uncertainty. Hi, Baji. So let's read this part, which will make all of this more clear. So there was a showdown between Einstein and Niels Bohr. And this will make clear to you what we're talking about. The showdown finally came at the 6th Solvay conference in Brussels in 1930. So now we're in 1930, so less than 100 years ago, not too long ago. What was at stake was nothing less than the nature of reality itself. Einstein hammered incessantly at Bohr, Niels Bohr, who reeled under the constant attacks but managed to ably defend his positions. Now remember, Einstein was very good at speaking. He was a very magnetic, charismatic speaker and presenter. Niels Bohr was more introverted. And of course, Einstein is already well known at that point, very famous, amazing theorist. People know him. A lot is at stake, and Niels Bohr is kind of struggling at this point. So finally, I mean, he's struggling because he's on the spot. His work is being questioned. It's like going through a defense. You know, everybody struggles when they're going through having to defend their work, say for a PhD defense. But this is maybe even more important because a very important theory is being discussed here. Okay. Finally, Einstein presented an elegant thought experiment, which he thought would demolish the demon, the uncertainty principle. So he's trying to demolish the uncertainty principle because Einstein and other people were not happy with this uncertainty business. They were trying to, thank you, Death Dragon. They were trying to demolish it, saying that, well, no, wait a minute. we can measure things. So there is no uncertainty. We don't want to accept that our uncertainty is now formalized and you're saying it's part of nature, but we don't want to accept that. We want to believe that we can do better. So let me give you a thought experiment, and you should explain to me about uncertainty in terms of this thought experiment, because it is more of a real scenario. So tell me about uncertainty with this real scenario. So what is that real scenario? Imagine a box containing radiation. There's a hole in the box with a shutter. When the shutter is opened briefly, it can release a single photon from the box. Thus, we can measure with great certainty the precise time at which the photon was emitted. Much later, the box can be weighed. Because of the release of the photon, the box weighs less. Because of the equivalence of matter and energy, we can now tell how much total energy the box contains, also to great accuracy. Thus, we now know both the total energy and the time of opening of the shutter to arbitrary accuracy without any uncertainty, and hence the uncertainty principle is wrong. Einstein thought he had finally found the tool to demolish the new quantum theory. The new quantum theory is, of course, this one which needs uncertainty, and he's trying to take down this uncertainty part. Paul Ehrenfest, one of the participants of this conference, he's also a well-known scientist. He participated in this conference, and so he was a witness to this fierce battle. He would write, "To Bohr, this was a heavy blow. At the moment, he saw no solution. He was extremely unhappy all through the evening, walked from one person to another, trying to persuade them all that he could, all that this could not be true. Because if E was right, Einstein, this would mean the end of physics." So this is how important this was to Bohr. He saw this from his perspective, which is the perspective that needed uncertainty. Because if you wrote down Schrödinger's equation as the wave equation of matter, and it turns out it's actually the probability of that position, that's how the wave equation would work. That then called for uncertainty. So then for him, the uncertainty principle and accepting uncertainty is very important, because he's one of the big contributors of quantum mechanics. Now, you can say that you don't believe it, but to him, this is very important. So when he did not, when he was not able to kind of win that argument, it's not so much that he didn't win the argument, it's that now he's afraid that people are not getting it and will not be contributing to the right thing towards that direction, and this could take down physics, basically, in his mind. It's very important. But he could think of no refutation. Like, he knows it's wrong what Einstein said, but he doesn't know how to prove it wrong. And that can be very difficult. And the thing is, when you're put on the spot, it can be kind of difficult to give a response. We've all been there. We've all defended our PhDs. And there's always that question at the end that you cannot answer and you think you'll fail. It happened to me, but thankfully I didn't fail. But there were a lot of other questions that I could answer. But there's always that one question on the spot that's very difficult. And it's like, oh, thank you. You should help me out and share the live and share my videos. Thank you so much. There's always that one thing that you cannot answer at the right time, and you beat yourself up about it. And it's like, oh, why couldn't I think it through in the moment? But in the moment, there's a stage, there's you, there's Einstein, and it's too much. You can't think everything through on the moment, on the spot. I will never forget the sight of the two opponents leaving the university club. Einstein, a majestic figure, walking calmly with a faint ironical smile, and Bohr trotting along by his side, extremely upset. When he talked to Ehrenfest later that evening, all Bohr could mumble was one word over and over again: Einstein, Einstein, Einstein. But after an intense sleepless night, Bohr finally found the defect in Einstein's argument, and he used Einstein's own theory of relativity to defeat him. Bohr noted that because the box weighed less than before, it would rise slightly in the Earth's gravity. But according to general relativity, so like if Baji's suddenly weighed less, he would rise a little bit in Earth's gravity, in the gravitational potential of the Earth. It would rise slightly in the Earth's gravity, but according to general relativity, time speeds up as gravity gets weaker, so that time beats faster on the moon, for example. So time beats faster on the moon because the gravity of the moon is weaker than on the Earth. Thus, any minuscule uncertainty in measuring the time of the shutter would be translated into an uncertainty in measuring the position of the box. So it is not the case that there was no uncertainty in measuring the position of the box. Why? Because now there is uncertainty in that time measurement, because there is uncertainty from the box's movement, because of the gravity changing. And so there is still uncertainty. It's not that Einstein, you said that the box position was known and the time was known, and so there was no uncertainty. He basically used relativity, which is Einstein's theory. So it's like everybody, no matter how smart, no matter how great, no matter how amazing, majestic, well-known, recognized, established, everybody has a blind spot. Everybody has a blind spot. Even Einstein had a blind spot. But then it's important to contribute great things, and it's important to learn those great things so that you can contribute more great things, because even the contributor of a great thing can miss something, even about their own thing. You know what I mean? It's amazing. That's why we have to learn physics, so that we can contribute, because if we don't understand and learn physics, we won't be able to know what is known. And if we don't know what is known, we cannot contribute. If we don't know what is known well, if we're not a good student of Einstein, like Niels Bohr, then we cannot catch the blind spot of Einstein. We cannot catch what Einstein's theory is saying to Einstein. So he used relativity. I'm so proud of him. Oh, amazing, amazing, absolutely magnificent. You cannot therefore measure the position of the box with absolute uncertainty. Furthermore, any uncertainty in the weight of the box will be reflected in uncertainty in its energy and also its momentum. And hence you cannot know the momentum of the box with absolute certainty. So because you knew the box's position, you cannot know the box's momentum with certainty. So any uncertainty in the weight of the box will be reflected in uncertainty in its energy and also its momentum, and hence you cannot. So basically, he said, Einstein thought that this box position and momentum, because it's sitting there, is known with certainty, and we know the time. Everything is certain, but that's not the case. There is actually an uncertainty, a very subtle uncertainty in this case, but there is actually an uncertainty in the time and how gravity affects this box with the change that happens in the box. And because gravity is changed and gravity affects how time moves, there's actually an uncertainty in the position, and there is an uncertainty in that's reflected in the energy and the momentum. So Bohr was right. Niels Bohr was right. He just couldn't reason all this out on stage at the conference in front of Einstein, but he used Einstein's theory to prove Einstein, you're wrong, I was right. This is the reasoning. You missed this. You skipped, you just didn't think of this. That there is a subtle way in which uncertainty is a part of this box business. When everything is put together, the two uncertainties identified by Bohr, the uncertainty in position and uncertainty in momentum, agree precisely with the uncertainty principle. Because not only do you say that there is an uncertainty, but you also have to make sure that it's quantified as what would be captured by the uncertainty principle, because uncertainty principle gives us an equation that can quantify the uncertainty. It's not just that you just say uncertainty. You have to make sure that that uncertainty lines up with what you would get from the uncertainty principle. Bohr had successfully defended the quantum theory, which of course had uncertainty, so that's what he's defending here. When Einstein complained that God does not play dice with the world, so God does not play dice with the world, that's Einstein talking about uncertainty in quantum mechanics. Chance, probabilisticness, the probabilistic nature of quantum mechanics. The fact that there was uncertainty now and it's formalized in the new quantum theory, this is God playing dice, and Einstein did not think that God would play dice with us, but God does at that small scale. When Einstein complained that God does not play dice with the world, Bohr reportedly fired back, "Stop telling God what to do." Oh, poor Bohr. This is very difficult to go against Einstein. Poor Niels Bohr. Can you imagine? God does not play dice with the world. Stop telling God what to do. At the quantum level, God can do what God wants. Who knows what God wants? This is what God wants. Uncertainty principle. Ultimately, Einstein had to admit that Bohr had successfully refuted his arguments. Einstein would write, "I'm convinced that this theory undoubtedly contains a piece of definitive truth." Commenting on the historic Bohr-Einstein debate, John Wheeler said, "It was the greatest debate in intellectual history that I know about. In 30 years, I never heard of a debate between two greater men over a longer period of time on a deeper issue with deeper consequences for understanding this strange world of ours." So we live in a strange world now with this 1930 timeline and going forward. You can imagine how strange it was for people then, because it's strange for people even now sometimes. And some of the repercussions of all of this. I'm gonna be back in 5 minutes. Okay, we can take a little break actually. I have to sip my tea anyway. The repercussions of the quantum theory, the repercussions of it being probabilistic, the repercussions of uncertainty will lead to more things. People were struggling to accept this new realm. So you can imagine, even now there's issues. Even now there are mind-boggling things sometimes that come from quantum. So it's important to understand what people's views were at that time, but also important to understand when something has been established and what the truth is. And to learn something well enough where you can understand that that's the truth, right? So that's where we're at. I'll take a sip of my tea while Death Dragon does their thing. Actually, the next paragraph is very funny because it has Schrödinger. So remember, Schrödinger was an... Oh, I need to be careful about this hot tea with Baji sitting here. Schrödinger, when he wrote down his equation, didn't think that it would give us a probability. He didn't like that it was a probability. It's so crazy. It's like you contribute to something and then you don't like it. When it gets too crazy, you know? Makes people, I think it made them feel very vulnerable. And how they would be known in history, you know? But that's the thing though, you can't control everything. That's the thing. But it made them feel some sort of way. Some type of way. Okay, one more sip and we'll keep going. and please feel free, if you're enjoying the live, feel free to share it with a friend or something. Maybe you can be here with the friend together. Together you can enjoy. Sorry, I'm using this like a mirror. Schrödinger, who also hated this new interpretation of his equations, proposed his celebrated problem of the cat to poke holes into uncertainty principles. So this is the thing about physicists and researchers. Even today when we work in these labs and stuff, a huge part of the business of doing this work, of doing research of any kind, is like you do your research, then you communicate your research, and then all of these other people try to poke holes at your work. And then you have to be okay with that, and you refute whatever holes they're trying to poke, or you defend it. Basically, you have to be in this mode of defense. It can be very uncomfortable. But that's kind of the bread and butter of physicists and scientists in general. I will just speak for physicists because I have most experience with physics and physicists. I've worked with physicists for a very long time. Poking holes at something is like their hobby. It's like what they do, you know? It doesn't matter what crazy thing they might have contributed. They will poke holes at whatever you're saying because it's part of that debate, that argument. They need to think everything through and understand everything and make sure it makes sense, and that it makes sense to them, that the thing has their blessing. So, Schrödinger was an early contributor to all of this, the new quantum theory. He's a contributor to the new quantum theory, but he's also poking holes at it. Just because. Because why not? Because he doesn't agree yet. He's not bought into the development of this uncertainty part of it yet. That's what's going on here. Schrödinger wrote about quantum mechanics. I don't like it, and I'm sorry I had anything to do with it. The most ridiculous problem, he wrote, was that of a cat sealed in a box. Oh, Baji, close your ears. We can't have Baji hear about this cat that's sealed in a box. Written by Schrödinger. Okay, I'm back. Okay, good. We're just about to talk about Schrödinger's cat, and so Baji's ears are closed. Baji, don't listen to this. It's very horrifying. The most ridiculous problem, he wrote, was that of a cat sealed in a box. Why would you seal a cat in a box? Inside which there's a bottle of hydrocyanic acid, a poisonous gas connected to a hammer triggered by a Geiger counter that is connected to a piece of radioactive substance. Okay, Schrödinger, weird and cruel thought experiment. There is no question that radioactive decay is a quantum effect. If the uranium does not decay, then the cat is alive. How dare you? How dare you, Schrödinger? But if an atom decays, it will set off the counter, trigger the hammer, break the glass, and kill the cat. How dare you? Baji's ears are closed. But according to the quantum theory, this is like a horror movie for us. But according to the quantum theory, we cannot predict when the uranium atom will decay. In principle, it may exist in both states simultaneously, both intact and decayed. Sorry, I can't read your comments. I know, right? There's some... Unbelievable. According to quantum theory, we cannot predict when the uranium atom will decay. In principle, it may exist in both states simultaneously, both intact and decayed. But if the uranium atom can exist simultaneously in both states, then it means that the cat must also exist in both states. We hope alive. So the question is the cat dead or alive? Baji? Baji's ears are closed. This is a horrifying example that Schrödinger gave us to refute the uncertainty principle, saying that it can't be right. But how cruel of an example he has used against cats. Unbelievable. Just unbelievable, Schrödinger. Okay, so that's Schrödinger's cat. It's a very famous cat example. This is Baji cat. Better off like this, Baji. Normally, this is a silly question. Even if we cannot open the box, common sense tells us that the cat is either dead or alive. One cannot be both dead and alive simultaneously. This would violate everything we know about the universe and physical reality. However, the quantum theory gives us a strange answer. The final answer is we don't really know. Before you open the box, the cat is represented by a wave, and waves can add, like numbers. We have to add the function of a dead cat to that of a live cat. How dare you? Thus, the cat is neither dead nor alive before you open the box. Sealed inside the box, all you can say is that there are waves that represent the cat both being dead and alive at the same time. Once we finally open the box, we can make a measurement and see for ourselves what the state is. I'm not liking this example at all. The measurement process by an outside observer allows us to collapse the wave function and determine the precise state of the cat. Then we know if the cat is blah or alive. The key is the measurement process by an outside observer by shining a light inside the box. The wave function has collapsed and the object suddenly assumes a definitive state. So now we're talking about measurement. And we know that when you measure something, you've changed its state. In other words, the process of observation determines the final state of an object. The weakness of Bohr's Copenhagen interpretation lies in the question, do objects really exist before you make a measurement? And that's okay if they don't. To Einstein and Schrödinger, all this seemed preposterous. For the rest of his life, Einstein would grapple with these deep philosophical questions, which even today are still the subject of intense debate. The thing is, can you say that objects really exist unless you've made a measurement? Maybe they don't. I'm making a measurement by giving Baji head scratches. That's why I know he exists. That's why I know he exists. Probability of finding Baji is high near me. But it's just a probability. Right, Baji? Where's your eye? Good job, Baji. Good job. You understand. Several upsetting aspects of this puzzle shook Einstein to the core. First, before a measurement is made, we exist as the sum of all possible universes. We cannot say for certain if we're dead or alive, or whether dinosaurs are still alive, or whether the Earth was destroyed billions of years ago. All events before a measurement is made are possible. Yeah. All events before measurement is made is possible. Yeah. Nicholas, hello. How are you? Nicholas from Georgia has joined the chat. All events before a measurement is made are possible. Second, it would seem that the process of observation creates reality. Thus, we have a new twist to the old philosophical puzzle of whether a tree really falls in the forest if no one hears it. If no one makes the measurement of it falling, then I guess it didn't fall. You know? That's how it be. I'm good. Yeah, better. This week has not been the most usual week for me. It's an unusual week, but yeah, doing good. Thank you for asking. A Newtonian would argue that the tree can fall independent of observation. Same thing, continuing the quantum mechanics discussion from last night. Just continuing from last night. Adding in some tidbits. So, I can see Baji's face. That's kind of nice. A Newtonian would argue that the tree can fall independent of observation. But someone from the Copenhagen school would say that the tree can exist in all position states. In all possible states, sorry. The tree can exist in all possible states: fallen, upright, sapling, mature, burnt, rotten, etc., until it is observed, at which point it suddenly springs into existence. Yeah. Thus, the quantum theory adds a totally unexpected interpretation. Observing the tree determines the state of the tree, that is, whether it fell or not. Einstein, from his days at the patent office, always had an uncanny knack for isolating the essence of any problem. The essence of any problem. He would therefore ask visitors to his home the following question: does the moon exist because a mouse looks at it? There's a full moon tomorrow. Maybe a mouse will look at it. If the Copenhagen school is correct, then yes, in some sense, the moon springs into existence when a mouse observes it, and the moon's wave function collapses. Yeah. Let me read your comments. You're a clone of mine. OTS fine. What happens in the darkness shall show itself in the light of day. Yay, full moon. Yeah. It's making me thoughtful about something, but yeah, we'll keep going. We'll keep going. We will keep on going. Over the decades, a number of solutions have been offered to the cat problem. None of them totally satisfactory. Although almost no one challenges the validity of quantum mechanics itself, these questions still remain as some of the greatest philosophical challenges in all of physics. So these types of questions about does the moon exist because the mouse looks at it, does the thing about the cat, or the tree, is it there if no one observes it? Is it not there? All of this stuff are sort of like philosophical questions. I would say that basically quantum mechanics was written, yay full moon, yeah, was formalized to describe the physics of the small scale stuff, electrons, protons, atoms, subatomic stuff. And it is true that if you shine a photon on an electron, you're going to change its state. You're going to give it some energy that it didn't have, and now you don't know its momentum. Or if you knew its momentum, you don't know its position. You know, it's true. Those things are true. It's not like this has to make sense also in terms of like a classical question, like a tree or the moon or us or a cat. Cats are classical, right, Baji? How old is Baji? Baji, what's your age? Baji will think about it and tell you. Baji will think about it and tell you. So, I think people loved to poke holes at quantum mechanics, and they were uncomfortable. They were uncomfortable with this whole, oh, Baji. Let me take a clip of your face, Baji. They were uncomfortable with this whole uncertainty principle stuff. They were uncomfortable with the probabilistic nature of quantum mechanics versus the deterministic nature that they're used to with classical physics. But the point is, anything that's formalized is for a reason. We were trying to formalize equations and a way to understand mechanics and write down how things work at the quantum level. So if that brings up philosophical questions like that of the cat or the moon or us, I mean, that's not really that important to me. I don't know why they were. I feel like part of it is an ego battle. There is a humane issue. Look at Baji's expression. Hi, Supri Wang. How are you? I know. Baji's enjoying this. There's sort of the human nature part of all this too. I feel like some of these things get blown out of proportion in terms of like what was given importance. Like all these philosophical questions about Schrödinger's cat, that whole scenario became very famous. It's almost like what people take away from quantum mechanics, but that's not the takeaway of quantum mechanics. Oh gosh, yeah. That's not really the takeaway of quantum mechanics. The takeaway for quantum mechanics is that it gives us a way to write things down and formalize the motion of particles and the behavior of particles. And that's okay. I don't feel the need to control things more than that. So I'm okay with it. How cool would it be if the flat earth theory was true? It's not observed to be flat, but if it were observed, that would be different. I've thought 100 times as much about the quantum problems as I have about general relativity theory. So this is Einstein. Of course, he gave us general relativity. So he thought a lot about general relativity. And he's saying that he thought about quantum mechanics just as much. Baji, where are you going? Look, Baji has gone over there now. He thought about quantum mechanics just as much, if not more, just because of all these questions. I've thought 100 times as much about the quantum problems as I have about general relativity theory, wrote Einstein about how he endlessly grappled with the foundations of the quantum theory. After much deep thought, Einstein fired back with what he thought was the definitive critique of the quantum theory. In 1933, with his students Boris Podolsky and Nathan Rosen, he proposed a novel experiment that even today is causing headaches to many quantum physicists as well as philosophers. The EPR experiment may not have demolished quantum theory as Einstein had hoped it would, but it succeeded in proving that the quantum theory, which was already pretty bizarre, gets weirder and weirder. Suppose that an atom emits two electrons. Oh my gosh. It's this down. Yeah. Okay. I've remembered what this is. All right, listen up. Suppose that an atom emits two electrons in opposite directions. Each electron is spinning like a top, pointing either up or down. Suppose further that they're spinning in opposite ways, so the total spin is 0. Although you don't know which way they're spinning. So these thought experiments are good because poking holes at something is okay, because you might actually discover some more things when you do that. You know, either you fail and you're like, okay, I was wrong because this other thing explains this, or it's like this debate may reveal further features of quantum mechanics and quantum theory, which may be proved right, and then it becomes even weirder. So even weirder is coming. One electron, so they're spinning in opposite ways, okay? So the total spin is 0. Spin is a property, a quantum property. Although you don't know which way they're spinning, for example, one electron may be spinning up while the other is spinning down. If you wait long enough, these electrons could be separated by billions of miles. Before any measurement is made, you don't know the spins of the electrons. Right. Now suppose that you finally measure the spin of one electron. It is, for example, found to be spinning up because you've measured it. Now you know it's spinning up at that point. Then instantly you know the spin of the other electron. Although it is many light years away, since its spin is the opposite of its partner, it must be spinning down. This means that a measurement in one part of the universe instantly determined the state of an electron on the other side of the universe, seemingly in violation of special relativity. Einstein called this spooky action at a distance. Spooky time. We just had Halloween. It means that some atoms in our body may be connected, the philosophical implications of this are rather startling. It means that some atoms in our body may be connected with an invisible web to atoms on the other side of the universe, such that motions in our body can instantly affect the state of atoms billions of light years away, in seeming violation of special relativity. I think this is what gave rise to the twin flame theory, by the way. Spiritual people love this. I'm spiritual too. But if physics gives you stuff like this, then can you imagine? Can't blame people for believing. So the Earth is moving at 10,000 miles an hour through space and rotating at over I don't know these numbers actually. I'm not the best. Well, spin is a quantum property of particles. We will get more into that It's different based on what type of particle. But this electron thing, because the electrons can get separated, Death Dragon says it's 2:35. Yep, same for me, Death Dragon. Same for me. But we'll keep going. I forgot about this example. It's actually... I'm going to think about this more. This is bizarre because the information, you know how people study quantum information, quantum computing, quantum this, quantum that. Why is that all so important and bizarre? It's important to understand this. It's important to understand this because this is what could be affecting our reality going forward. And an understanding of how quantum stuff works, that's sort of what's coming in our technology, right? So we should understand this. And if there's a mistake in any of this, it's not too late to contribute because everything is very bizarre going forward in all of this. This stuff is becoming bizarre. So either you're like, oh, this is bizarre, I don't believe it, well, find the problem and discover and give us a different solution, or you take bizarre and you run with it, and it's like, if the two electrons got separated and became light years apart and the spin of one is measured and it's up, it instantly determines that the spin of the other one is down because the total has to be zero. Because of conservation. So because in the beginning you knew that the total spin was zero, at any given point going forward, the total spin still has to be zero. That's the point of that. Now, I don't know if there's any other physics involved that would affect things. And this is only a thought experiment. But it means that you've measured something by measuring this electron that you're near and measuring that its spin is up. Baji, did you fart in my face? Oh my God. I think Baji has farted in my face and then sat down on me. There's some electrons I didn't need right now. It's because of conservation. If you measure the one that's near you and you know it's up, the problem is that you instantly know the spin of the other one. That's the problem. That's what people didn't have. That's what people don't like. That's what I don't like, actually. I don't like it. I don't like it. Actually, I don't like it. Oh my God. It's been known for almost 100 years, but I don't like it. That you would know the spin of the other one, the other electron, even though it's moved far away, and it could be really far away, unless that's not allowed somehow. Maybe that's not allowed somehow. Maybe there's something disallowing it from moving so far away, and then information traveling instantly. It's like because you've measured the spin of this one, you've also measured the spin of that one, but that could be really far away, and you're measuring the information about that one instantly. That's the problem. That's the problem. Oh, is this about the flat? Oh my God. No, the earth is not flat. No, 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 no. We know that. We know that. Oh, I wish. I wish things were so simple. We know that the earth is not flat. My friend, we have observation from space. It's not flat, dear. Sorry. I'm more. I knew this problem about the two electrons, but I kind of forgot. And it's kind of dawning on me again. This is why quantum theory is so popular again in like the spiritual community. And this twin flame stuff and soulmate, and it's because of this part that we're reading. So pay attention if you want to understand your twin flame. I'm not an expert in that, but here's spin. Einstein called this spooky action at a distance. The philosophical implications of this are rather startling. It means that some atoms in our body may be connected with an invisible web to atoms on the other side of the universe, such that motions in our body can instantly affect the state of atoms billions of light years away. In seeming violation of special relativity, which, by the way, remember said you can't travel faster than the speed of light. Information was not really allowed to travel faster than the speed of light until now, but this thing is suggesting otherwise. Einstein disliked this idea because it meant that the universe was non-local. That is, events here on Earth instantly affect events on the other side of the universe, traveling faster than light. So this whole thing, Einstein disliked that this would mean that the universe was non-local. And this whole, I mean, it is disturbing to think that something happening here can affect something happening very far away, millions, say, light years away. But the problem is not that. The problem is that it's instant. The fact is, as soon as you know the spin of the electron here, you would know the spin of the other one, no matter how far away it was, instantly. This instant part is the upsetting part. It could be a lie, scientists. Ooh, you could go to space and see it for yourself, Nicholas. How about that? If you become an astronaut and go to space, you can see that the Earth is round. Ice walls in Antarctica. Wait a minute. It could be a lie. The scientists have already proven that there's a firmament in the sky. There's a firmament. Oh, I don't know what that means. That we're not allowed to leave this Earth. You can also see it from a plane, actually. You can see the... Have you flown in a plane? You can kind of see it from a plane, depending on how far up and the horizon, the bending of Earth. And the ice walls in Antarctica. What about the ice walls in Antarctica? There's definitely a lot of ice in Antarctica. I've been there. So my PhD project was in Antarctica. So if you have any questions about that, let me know, because I've been there. But I am upset as well. This thing that Einstein is upset about, I am also upset about this, because knowing something instantly is not allowed. But I guess it is. We'll keep reading. Nicholas, there are bigger questions. There are harder questions. I hate to break it. There are harder questions that we must find the answers to. On hearing of this new objection to quantum mechanics, Schrödinger wrote to Einstein, "I was very happy that in that paper you have evidently caught dogmatic quantum mechanics by the coattails." This thing about the electrons. Hearing of the latest Einstein paper, Bohr's colleague Leon Rosenfeld wrote, "We dropped everything. We had to clear up such a misunderstanding at once." Bohr, in great excitement, instantly began dictating the draft of a rejoinder. Oh my gosh, I've completely forgotten about this part, so I'm excited. Oh my god, that's right! Oh my god. Oh my god, oh my god, oh my god. A very exciting part is coming up. The Copenhagen school withstood the challenge. So, Einstein gave them a challenge, which is that how do we know the spin of the other electron instantly? We know the total spin has to be 0, so you're telling me by measuring the spin of this one, you know the spin of the other one instantly. And I have an issue with that because that other electron could have traveled very far away, and you're telling me that this information is available to us instantly. That's the problem. Baji is so cute. Oh, thank you. Thank you. But Bohr was ready for this challenge. Let's read about that. Bohr had to concede to Einstein that the quantum universe was indeed non-local. That is, events in one part of the universe can instantly affect another part of the universe. Wow. Everything in the universe is somehow meshed together in a cosmic entanglement. So the EPR experiment did not disprove quantum mechanics, it only revealed how crazy it really is. Over the years, this experiment has been misunderstood with scores of speculations that one could build EPR faster than light radio, or that we can send signals back in time, or that we can use this effect for telepathy. So I think this is where the confusion is coming from. Some of the things that they thought about or the things that they debated about in quantum mechanics led to some misinformation being spread about quantum mechanics as well. So I wanted to mention that. Yeah, so this quantum entanglement, you might have heard about entanglement in dating as well. Some people talk about we're in an entanglement. That's where this is where that comes from, just so you know. Quantum mechanics. You can blame your dating issues, spiritually, all that twin flame stuff on quantum mechanics. That's where that comes from. According to, I don't know, don't quote me. The EPR experiment did not negate relativity, however. In this sense, here we're just talking about physics. The other comments are, take it with a grain of salt. The EPR experiment did not negate relativity, however. In this sense, Einstein had the last laugh. No useful information can be transmitted faster than light via the EPR experiment. For example, you cannot send Morse code faster than light via the EPR apparatus. Physicist John Bell used this example to explain the problem. He described a mathematician called Bertelsmann who always wore a pink sock and a green sock. If you knew that one foot had the green sock, you knew immediately that the other sock was pink. Big breath. Yet no signal went from one foot to the other. So it's kind of like because we know one thing, we know the other thing. The pink sock means that there is the green sock on the other side. Here's Baji Baji. So maybe we have broken through the firmament. Isn't it weird how technology has gotten so good within the last 100 years? What did they really find on the moon? I don't know what you mean. What do you mean? Which mission are you talking about? So, If you knew that one foot had the green sock, you knew immediately. Hi, Death Dragon. Look at Baji's face. You knew immediately that the other sock was pink. Yet no signal went from one foot to the other. In other words, knowing something is entirely different from sending that knowledge. Oh, this is nice. It's almost like we know something, but it's not like we've received a message about that thing. Like maybe we know that because we measured the electron spin to be up here, the pair electron, the other electron in the pair's spin, we know is down. But that does not mean that some information was transmitted to us. So knowing something is different than sending that knowledge. So there is a world of difference between the possession of information and its transmission. So basically, relativity tells us that information is still transmitted. The biggest speed at which it can be transmitted is still the speed of light. Nothing can go faster than that. So it's not that we have measured the spin of that other electron to be down just because we have measured the spin of this one. We know the spin of the other one is down because we measured this one. It's not like we measured that one and transmitted that information to us instantly. If that makes sense. I like that. I think I'm good with this. I like that. Greetings from Turkey. Hi, Turkey. How are you, Conquer Kepix? Thank you for joining. Thank you for... Here am I. Sorry, Turkey. I got too excited and made YouTube app shift from the screen. Here is Baji. There is a kitty cat here and a book and me. Oh my god. If the phone will stay still. Knowing something is entirely different from sending that knowledge. There's a world of difference between the possession of information and its transmission. No one said anything about transmission, Einstein. No one said anything about transmitting the information about the spin of that other electron through light years of distance instantly. We just know instantly. We haven't measured and transmitted that information. Okay, that's very reassuring, at least to me. Thank you, God. By the late 1920s, there were now two towering branches of physics, relativity and the quantum theory. The sum total of all human knowledge about the physical universe could be summarized by these two theories. One theory, relativity, gave us a theory of the very large, a theory of the Big Bang and black holes. So I was telling you, right, that the physics of the very large and the physics of the very small are two different realms. When people are used to one, they might not be used to another one. They might have difficulty getting used to another one. But here we are. So the sum total of all human knowledge about the physical universe could be summarized by these two theories. One theory, relativity, gave us a theory of the very large, a theory of the Big Bang and black holes. The other theory, the quantum theory, gave us a theory of the very small, the bizarre world of the atom. Kitty, says Death Dragon, thank you. Although the quantum theory was based on counterintuitive ideas, no one could dispute its stunning experimental successes. Nobel Prizes were practically flying off the wall for young physicists willing to apply the quantum theory. Einstein was too seasoned a physicist to ignore the breakthroughs being made almost daily in the quantum theory. He did not dispute the experimental successes of it. Quantum mechanics was the most successful physical theory of our period, he would admit. Neither did Einstein impede the development of quantum mechanics as a lesser physicist might have. In 1929, Einstein recommended that Schrödinger and Heisenberg share in the Nobel Prize. Instead, Einstein shifted strategies. He would no longer attack the theory as being incorrect. His new strategy was to absorb the quantum theory into his unified field theory. Because remember, this chapter is about the unified field theory. Oh, hi, Michael. Hello and greetings from Germany. Guess what? We're reading about Einstein, who was also from Germany. Thank you for chatting. So Einstein was warming up and obviously recognizing that the quantum mechanics was, was proceeding, it was progressing. There was progress being made. There was, Nobel Prizes being won. There was experimental successes of it. And no matter how bizarre it might be, no matter how... Yes, indeed, we're reading this book. No matter how bizarre it might be, it was successful, and that's what mattered. Experimental success is what rules physics. So, we'll keep going. And remember, in this same chapter, what we talked about is the unified field theory and all the efforts to sort of unify electromagnetism with relativity, which included special theory of relativity, as well as general theory of relativity. Many people view this critically. Yeah, possibly. So anyways, when he would no longer attack the theory as being incorrect, his new strategy was to absorb the quantum theory into his unified field theory. When the army of critics in Bohr's camp accused him of ignoring the quantum world, he fired back that his real goal was nothing short of cosmic in scope, to swallow up the quantum theory in its entirety in his new theory. Because, depending on who's working on what, a field can sort of suffer a type of negligence or neglect. And I think Bohr and his camp was like, well, wait a minute. Don't ignore us quantum physicists, work with us or help us to progress quantum physics and quantum mechanics, because if it gets cornered, if it's pushed to the side, then it will not have as much progress. And if it's not accepted by someone really big, then it will not have the progress that it needs. And the people kind of proposing those things, hypothesizing those things, even though they're very successful, they still want to be mainstream and have mainstream level of acceptance so that the field can progress further. Because nothing is ever done. Everything is always, still has to progress. So then Einstein was like, well, I'm trying to unify everything with my new unified field theory. Based on the theory of relativity, you can say pretty much anything. Okay, like what? Okay, so Einstein used an analogy drawn from his own work. Relativity did not prove that Newtonian theory was completely wrong. It only showed that it was incomplete. That it could be subsumed into a larger theory. So Newtonian mechanics, of course, it works well in the classical scales. So Einstein is saying, well, Newtonian theory is not wrong. It's just a subset of my relativity theory. It applies very well in classical scenarios. I'm just saying that with relativity, I can capture more. Thus, Newtonian mechanics is quite valid in its own particular domain, the realm of small velocities and large objects. If the scales are different, like classical scales, large objects, smaller velocities, as in velocities much smaller than the velocity of light, is what that means. Then it's good. Then it's valid. Oh wow, Baji has climbed up very high. Usually he does not. Similarly, Einstein believed that the quantum theory's bizarre assumptions about cats being dead and alive simultaneously could be explained by a higher theory. So he was hoping that there is some bigger theory, some higher theory, which would come in and kind of subsume quantum mechanics, give us a bigger meaning of quantum mechanics, a bigger understanding of quantum mechanics, a bigger theory that can capture it and perhaps give us more physical insights altogether, just like his relativity did for classical mechanics. That's what he was hoping the unified field theory would do. Yeah, I got it. In this respect, legions of Einstein's biographers have missed the point. Einstein's goal was not to prove the quantum theory incorrect. As many of his critics have claimed, he has too often been painted as the last dinosaur of classical physics, right? Because after that, we also have particle physics, we have more and more things coming out in the direction progressing quantum field and physics of the very small. So the author, Michio Kaku, is saying that Einstein is too often known as the last dinosaur of classical physics. That's not necessarily the case. Oh, no worries. Say whatever you like in the chat. In this respect, legions of Einstein's biographers have missed the point. Einstein's goal was not to prove the quantum theory incorrect, as many of his critics have claimed. He has too often been painted as the last dinosaur of classical physics, the aging rebel who found himself becoming the voice of reaction. Einstein's true goal was to expose the quantum theory's incompleteness and to use the unified field theory to complete it. In fact, one of the criteria for the unified field theory was that it reproduce the uncertainty principle in some approximation. Because he accepted that uncertainty was part of life, it was part of physics at this point with quantum mechanics, he wanted the unified field theory to capture that, to basically be the more general theory that can capture quantum mechanics and relativity and everything. So that's what he wanted. So let me read your comments now. Based on the theory of relativity, you can say pretty much anything. Got it. Okay. That's true. There's a lot of things that come out of relativity. It's the more updated theory of gravitation, light, and we have seen a lot of experimental evidence and predictions coming true, even in very recent times. If we could leap through the quantums, how bad would it change reality on Earth? Better yet, if we leaped through the quantums, would Earth even exist? What do you mean by leaped through the quantums? And I don't know. I think, do you mean leap through times or going a large distance? Yeah, I don't know. What do people think about that? I don't know. Important philosophical questions do come out of this discussion. That's true. We'll keep going. I just realized that this chapter, very little bit is left. So we'll keep going. We'll finish it. So, the unified field theory is not something that came true, is not something that materialized. But we're talking about his approach in the matter, which is important to understand because maybe we could maybe do it. We could maybe work on it ourselves. Einstein's strategy was to use general relativity and his unified field theory to explain the origin of matter itself, to construct matter out of geometry. In 1935, Einstein and Nathan Rosen investigated a novel way in which quantum particles, such as the electron, would emerge naturally as a consequence of his theory rather than as fundamental objects. In this way, he hoped to derive the quantum theory without ever having to face the problem of probabilities and chance. Because remember, he didn't really like the probabilities and chance thing. In most theories, elementary particles emerge as singularities, that is, regions where the equations blow up. Think of Newton's equations, for example, where the force is given by the inverse square of the distance between two objects. When this distance goes to zero, the force of gravity goes to infinity, giving us a singularity. Because Einstein wanted to derive the quantum theory from a deeper theory, from a more general theory. What is that more general theory? Is what he's asking. He reasoned that he needed a theory totally free of singularities. Examples of this exist in simple quantum theories. They're called solitons, and resemble kinks in space. That is, they are smooth, not singular, and they can bounce off each other and maintain their same shape. Einstein and Rosen proposed a novel way to achieve such a solution. They started with two Schwarzschild black holes defined on two parallel sheets of paper. By using scissors, one could cut out each black hole singularity and glue the two sheets back together. Thus one obtains a smooth, singularity-free solution which Einstein thought might represent a subatomic particle. Thus, quantum particles can be viewed as tiny black holes. This idea was actually revived in string theory 60 years later. So, string theory is more recent. That also apparently talks about this, where there are mathematical relations that can turn subatomic particles into black holes and vice versa. The Einstein-Rosen Bridge. However, so this is Einstein-Rosen Bridge, however, can be viewed in another way. It represents the first mention in the scientific literature of a wormhole that connects two universes. Wormholes are shortcuts through space and time, like a gateway or portal that connects two parallel sheets of paper. The concept of wormholes was introduced to the public by Charles Dodgson, otherwise known as Lewis Carroll, the Oxford mathematician and most famously the author of Alice in Wonderland and Through the Looking Glass. When Alice puts her hand through the looking glass, she is in effect entering a kind of Einstein-Rosen bridge connecting two universes, the strange world of Wonderland and the countryside of Oxford. It was realized, of course, that anyone who fell through an Einstein-Rosen bridge would be crushed to death by the intense gravitational force enough to rip their atoms apart. Passage through the wormhole to a parallel universe was impossible if the black hole was stationary. It would take another 60 years before the concept of wormholes would occupy a key role in physics. eventually Einstein gave up this idea, in part because he could not explain the richness of the subatomic world. He could not entirely explain all the curious properties of wood in terms of marble. Because remember, he had an analogy with wood and marble. There were simply too many features of subatomic particles. For example, mass, spin, charge, quantum numbers, etc., that failed to emerge from his equations. So, like, his equations where the subatomic particles are now black holes, those have to give us all the quantum properties that we know about, like mass, spin, charge, quantum numbers. And it's difficult to get that all coming out of this theory that he's trying to come up with. His goal was to find the picture that would reveal the unified field theory in all its splendor. But one crucial problem was that not enough was known at that time about the properties of the nuclear force, because there's also the nuclear force that would also be part of the unified field theory, but Einstein was before that time. Einstein was working decades before data from powerful atom smashers would clarify the nature of subatomic matter. As a result, the picture never came. So that's the end of this chapter. The unified field theory is incomplete. It's still not a thing, but that's what Einstein was working on, is to have this unified theory that can explain electromagnetism, gravitation, quantum mechanics, and especially because he had these confusions, he had these problems with quantum mechanics, he was hoping that now, even though quantum mechanics made all these progresses and it was very successful experimentally, and there were camps that were defending quantum mechanics theories and findings and ideas, and even though there were bizarre parts to it, some camps were very much in favor of quantum mechanics and its bizarreness, and Einstein's camp was more like, well, can we find a more general theory from which all of this can just kind of fall out, and maybe we don't need the probabilities and the uncertainties, and there's a more deeper, I think he was looking for a more general, deeper physical insight. You know what I mean? He really loved to picture everything in a simple way and get a more deeper nature insight from it. Some of the stuff with quantum mechanics, I think, was worrying him because he wasn't sure about the physical implication and insight that you would get from it. So he wanted it from a more unified field theory, but then at the same time, strong force wasn't known about at that time. They didn't have the data on the strong force, which is something acting within the nucleus. So, the point is that he was ahead of his time. It was difficult to come up with unified field theory if you didn't have all the pieces of the puzzle. But at any given time, we only know what we know, and we can only do what we can do. And you have to trust other people to also work on things. So I think what we learned is that there's a lot of collaboration. People have blind spots, and the same people who might contribute to a field may have an issue with it, and then it's up to somebody else to contribute, I feel bad that the unified field theory was not a thing yet in his lifetime. It's still not a thing, but I'm sure it was upsetting for him to not realize it in his lifetime. But he did a lot of things. So, good job, Einstein! He did a lot of things, just not the unified field theory. So, that was this chapter. I'm kind of sad that the unified field theory did not come true yet. And even now, it's not a thing yet. Let's also remember that the top questions of the universe at this time, right now, is the nature of dark energy, which came up also in this chapter as, or maybe it was the last chapter, where he needed to introduce something called the cosmological constant in order to make the universe sort of stabilize. And by he, I mean Einstein, and work against gravity. Now, in today's date, we know that the universe is not only, you know, stabilized against gravity, but it's also expanding, and its expansion is not just happening, it's also accelerating. So that phenomena is given the name of dark energy. We still don't know exactly what that is. That is the one of the top mysteries of this universe that we can try to solve ourselves. And the next top mystery of the universe is, of course, the nature of dark matter. Both of these things have the word dark in them, but they're two different things. Dark matter is the other big question among big questions. So all of this stuff that we're learning will hopefully go towards our updating our understanding of what we do know and help us to contribute to the mysteries of the universe. Hopefully this was helpful. We will pick this up next time. Let's see what the next chapter is called. The next chapter of this book by Michio Kaku is, so this is Einstein's Cosmos by Michio Kaku. Thank you to the author for this awesome discussion and for helping us to learn all of this or study all of this in an accessible manner. And this has also given us a chance to discuss these topics. The next chapter is called, it's chapter 8. It's called War, Peace, and E equals MC squared. So it might be less mind-boggling because we just covered the more bizarre stuff, like quantum mechanics in the chapter we just covered. As we know, E equals MC squared, and the atomic bomb is, well, hi, Tu. How are you? The atomic bomb was also a thing at this time coming up. I find it to be less interesting than some of these other topics, but it is a reality of this time. But we'll learn about those things in the following chapter. Okay. Oh, I think the next chapter is gonna have some sad parts, guys. I've got this. It started the final phase of his life. We will kind of read about the final phase of his life. He aged rapidly. In the 1930s and 1940s. Aww. So I think we'll find about Einstein coming to force in the next chapter. Oh, but you know, the world wars and all of that is gonna be part of the story here. Oh, cosmology. Yeah. Oh. You know what I realized is that when he was living, all these all these big developments in cosmology didn't really happen yet. They're happening now. It took so long. Dark energy survey, dark energy spectroscopic instrument, those efforts are a thing now. And even then, we're still working on it, you know? I feel bad that he didn't see all this. There's still a lot of chapters, there's still a lot of material left in this book. We'll cover it. We'll cover it. We will cover it. Tomorrow we will go live earlier. It's Physics Friday. I've been doing physics every day, but, or covering physics topics every day, but tomorrow is very important because tomorrow is Physics Friday. Oh yeah. Okay, I was gonna see if there is talk about fermions and bosons later on in the book. And stuff like SUSY, supersymmetry. Oh my God. It's gonna be fun, guys. It's gonna be real fun, actually. Because I've kind of refrained from getting ahead of the time that we were covering and not talk about the stuff that we know now. Because it's more fun to discover it like this, in order. It'll be fun for me too, because it'll bring back some of the other work that I was doing at one point. Oh, good. So from here on, the rest of the book is just notes. Aw, like the... I see. So there's only a couple of chapters left. We're close. We'll probably finish this in like a couple days here. But apparently we'll get into supersymmetry. Death Dragon! We just finished chapter 7. And the conclusion was that the unified field theory was not done yet. And the next chapter we will cover is chapter 8. It's called War, Peace, and E equals MC squared. And there's going to be some sad topics in this one, such as the war and some other things too. Anyone know about string theory? Because a lot of the stuff that we talked about in this past chapter that we just finished, those higher dimension stuff, the black holes being subatomic particles, basically particles being a type of black hole, is something that comes up again in string theory. So he was going towards something. Him and his grad student started to sort of work on something that they might not have succeeded with, especially to come up with all the properties of quantum mechanics. Quantum mechanics, it's a whole field. It's not just You know E equals mc squared. Yeah, it's his most famous equation with a sad use of it. But um what was I just saying? It's it was hard. Quantum mechanics and all of its intricacies, all of the properties of quantum particles, charge, spin, mass, all of that is hard to like fall out of a theory that you tried to come up with, which is a bigger theory that can explain everything. It's hard to do that. Quantum mechanics is a whole field. It takes a year to teach quantum in undergrad and another year in grad. It's a whole domain, you know, it's a lot. I'm glad that so many other people were working and it gave us so many advances in quantum mechanics. That's why it's important to not depend on one guy to do everything. We have to depend on all of the guys and the gals to work on things because it's very hard. All of these problems are very hard. So the more of us that can work on these matters, the better. And we can make great strides, leaps and bounds, and make progress. Okay. How's everybody doing? Thank you for joining for the discussion today. Thank you so much. We've been discussing quantum mechanics mainly today and some of the bizarre discoveries of the field and how some people had an issue with it, but they still had to kind of accept it, about the unified field theory and it not really being finished. And tomorrow we'll pick up with this topic, war, peace, and E equals mc squared. It'll be a little depressing. Thank you. I like your jacket. Purple is my favorite color. Thank you. Is there UFO news, Heike? Tell me. First of all, Heike, thank you for being here. I'll read your message. It's always such a fun one. Thank you for reading and explaining quantum physics and cosmos. Good night to Baji and science friends. UFO news, guess what? We're not alone in universe. Is there UFO news? What is it? I haven't heard about it. Tell me. Tell me. Tell me. Or do you mean the... What do you mean? I know there was some news. What the sigma? Which news are you talking about? Let me find it. Let me go to Google. Is there any UFO news? We all could be living in a simulation. Yeah. Let me type. Is there a UFO news? What is the meaning of this, Heike? Oh, I see. Pentagon. Pentagon received hundreds of reports of new UFO sightings. Oh, that's right. Okay, there's a news item on this. You know, if I saw a UFO, I don't know if I would tell the Pentagon. That looks like a UFO message right there, Death Dragon. The Pentagon has received hundreds of reports of new UFO sightings, including several particularly interesting cases, according to the director of the universe, or director of the office. It's amazing how much power the mind has over the body. Yeah, indeed. Okay, it's not verified, right? It's not verified. Um, the topic of the UAPs. Hi, Mia. How are you? It's important to underscore that to date, AARO has discovered no verifiable evidence of extraterrestrial beings, activity, or technology. None of the cases resolved by AARO have pointed to advanced capabilities or breakthrough technologies. Boring. Aliens are not verified yet, my friends. That's okay. Wait. There's something about... Oh, the Pentagon released a new report on UFOs that revealed hundreds of documented incidents of unidentified and unexplained aerial phenomena. Okay, so this is called UAP, unexplained aerial phenomena. Let me see your comment. No aliens, says Death Dragon. Pie. I like that comment. Pie. The end will be closer tomorrow. Oh my god. That's quite troubling. Nicholas, don't tell me. Don't tell me. Okay, now my thing won't load. Nothing's working anymore. Maybe there is a UFO in town. My iPad stopped working. Well, I think it's because it can't handle it. It can't handle it. Okay, they released a report, looks like. Whatevs. All right, guys. Tomorrow we will meet for Physics Friday. Yes. Okay. Delhi has had bad smog. I believe that. More than the UFO, I believe that Delhi has had bad smog. I've breathed that smog. So, with experimental evidence, I believe you. Delhi, Kolkata, right now? OMG. Right now, November, December, January, it's so polluted. It's hard. When I was in Kolkata last 2023, January, I was in Kolkata in India. Oh my God. The pollution, it was very hard to breathe there. People are like, how was it? I love it there. Other than the breathing part, food is great. Food is great. Everything is great except for the breathing of pollution. Where is Baji? Baji has gone upstairs. Unfortunately, Baji has now retired to bed. It's his bedtime already. So he's no longer hanging out with me anymore down here. He has decided that it's bedtime and no more. No more. Yeah. The weather. Okay. Now I'm yawning too. Baji has gone upstairs to bed. Weather is cooler during smog. Yes, exactly. And it's also like wedding season there. Oh, my phone's about to die. If this live goes away, it's not an alien invasion. My phone died. So blame Apple. If this phone dies and the live stream goes like, it's an alien invasion. Or Apple. We won't know until it's measured. It'll be uncertain until measured. Where's Baji? He has gone to bed. He believes in the Eastern Standard Time.